Is it visible?
Yes, sir.
Yes, sir.
View. So before moving into the deletion problem, let's just recap uh, the exercise I had given. Hopefully, all of you have been able to solve that. This is a simple example. The example could be found in CLRS book also. Okay, so that already we have the tree, partially constructed tree. Now we have to insert these 4 keys one by one. Then how they will be inserted. So insertion of B would take place first. So now since it is B tree of order 6, that means the maximum number of children would be 6. Okay. So maximum number of elements will be 5 in a node, and minimum number of children will be 3. That means minimum number of element will be 2. Fine. So when we insert B, B will first will compare here. So since B is less than G, so we need to follow this branch, leftmost branch, and then we come and hit at the leftmost leaf, where we can still insert one more element because only 4 elements are there. The maximum limit is 5. So we'll be inserting B here. So after insertion of B, the modified tree would look like this. Then element Q. Now Q is basically when we compare the value Q with the values available in the root node, we find that uh, Q appears between P and X. So we need to follow the second from the right. Second from the right branch. So we'll come to this particular leaf which is already filled. So before we insert, we should split it because it is having already maximum capacity is occupied. So we have to split it first and then we'll be able to insert Q. So without loss of generality, we'll move T up, and so it will be like this. T will be moved up and will be placed in between P and X like this, and then Q will be inserted. Since P and Q, see this particular node, the third from the right, QRS. Okay, so these 3 sub steps actually is needed to insert Q. Then L. Now when we any element, now whatever may be the value of the element, since we start with the root and root is already occupied, I mean it is already occupied by maximum number of elements. So before thinking of any insertion, we need to split it. Because this is a single pass insertion, we will always proactively split any already full node we encounter during our search path. Okay, so we'll be splitting it. So P will be prompted up, and the height of the tree, in this case since root is get split, height of the tree will be increased by 1 like this. This will be the change, and then L will be inserted. Since L is less than P and L is in between G and M, so L will be inserted in the node, leaf node, which is second from the left. So it will look like this. Finally, F will start from P. Since F is less than P, will follow the left branch. Now F is also less than this G, so we'll follow the left branch, but unfortunately this leftmost node is already filled with the maximum possible element. So we have to split it first like this, and then we'll insert F here. Second from the right node. Okay. So this completes the insertion of all those 4 elements. So is it okay? Everyone has got this one? Hello?
Yes, sir.
Uh,
Yes, sir.
Yes, sir.
so, okay. Now let us move into the deletion process. So as usual, deletion will start from uh, actually finding out that whether uh, I mean uh, whether it is a leaf or it is non-leaf. Okay. As usual, as you have seen in case of binary search, any version of binary search tree, because first of all, we need to ensure that after deletion, the modified tree must maintain the MOA search property. Okay. So if it is not leaf, then we need to replace that with the in-order predecessor or successor following the MOA search. Since it is a MOA search tree, it is built on B tree is built on MOA search tree. So we need to ensure MOA search property, and accordingly we have already seen that it is just a natural extension of uh, binary search tree, and accordingly we can here also find in-order successor predecessor. If it is a leaf node, then it's fine. But if the node to be deleted, not the node basically, we will be asked to delete an element. Okay. Now that element will be part of a node. Now we have to locate the node. If the element resides in a leaf node, then first step of deletion is very trivial. We'll delete it from there. No problem. But if it is not a leaf node, it is an internal node, then we need to replace that element with the in-order predecessor or successor, and then we have to actually delete the in-order predecessor or successor from its original place. Okay. And as we have seen, um, that in case of binary search tree, any arbitrary binary search tree, in order predecessor and in order successor cannot have both the children. Similarly, in case of AVL tree, where we have further more restriction about the difference in height of the left subtree and right subtree of any node, there we have found that in order successor or predecessor cannot have any child. I mean, it will always be a leap. So actual deletion would take place from the leap node itself. Similarly, since this if you look into the structure of any B tree, uh, since all leaves are at the same depth, you will find that in order successor or in order predecessor of any node must be a leap. So your actual deletion will always be from a leaf node. So either you are asked to delete an element which resides in a leaf, or even if you are asked to delete an element which is not present in a leaf, it is present in an internal node, but still actual deletion will take place from a leaf node, because what you will do, you will replace the replace the actual element to be deleted with its in order successor or predecessor, and you will actually physically delete the element from its original place. That in order successor or predecessor from its original place, which is a leaf, obviously. Okay, so actual deletion would take place irrespective of whether you are asked to delete an element which resides in leaf or not. Your actual deletion will always take place from leaf node. Is it okay?
Yes, sir. Yes, sir.
Okay. The next step, so it will be a two-step process, since we should not only ensure MOA search property uh, remain satisfied after deletion, but also we need to ensure that the other properties of B tree must be satisfied after deletion. Now the other property says that main property that we need to take care in deletion is we should not lead to an underflow. Like insertion, we are bothered about overflow, because every node is having a maximum capacity and a minimum capacity based on the value of m or order of the B tree. Like in case of 2-4 tree, which we are using for illustration, the maximum number of element is 3 and minimum number of element is 1. Okay. So in case of insertion, we need to check whether the insertion of a new element in a node exceeds its capacity. Then we have to split and do take care of the thing, as we have already seen. And in case of deletion, what may happen that we are deleting an item or element from a node now, which was earlier containing the minimum possible number of elements. Now it will lead to an underflow. But we cannot leave that in that condition. We must do something so that this underflow can be taken care of. Otherwise, it won't be representing a B tree at all. Okay. So that is very crucial. And that can be done in two different ways, depending on the situation. One is redistribute and second one is merge. Now, first one we'll try. If redistribution is possible, we'll redistribution. Now, what does redistribution means? Suppose I'm explaining with a figure later, but for the timing, just try to visualize. You are deleting one element from a particular node, the delete node obviously, which gets underflowed. That means it is now having, after the deletion, it is now having less than the minimum number of elements that should be there. Now this leaf node must have siblings. It can have left sibling, right sibling, both or anyone. Now if you find that any one of its sibling, left sibling or right sibling, has some extra element, extra means more than the minimum requirement, then you can borrow that one element. This is the concept of redistribution. You can borrow in a proper manner such that the B tree property remains satisfied in the entire tree. I'll show how it is possible. Now, sometimes it may so happen that it is not possible, that both the siblings, left and right, they are also having just minimum number of elements. They are not having any extra. So they cannot provide any element as borrow. Okay. I mean the node from where we have deleted cannot borrow from its siblings, because in that case the sibling may become underflow. Okay. In that case, we need to merge. Merge means we will merge that node which has gone underflown, its parent as well as its sibling, any one of the sibling, in order to prevent this underflow remain at ease. Let me illustrate using some figure and then I will illustrate with real example of 2-4 tree. So in case of 2-4 tree, a leaf L becomes empty after deleting the tree because the minimum is 1 here. So although I am illustrating using 2-4 tree, this is true for any B tree, just the value, the number of elements, number of minimum and maximum will vary here. Okay, since here m is 4, that's why the maximum is 3, minimum is 1. But for m is 6, maximum will be 5, minimum will be 2. Okay, like this. So in case of 2 4 tree, a leaf L becomes empty after deleting the key. Okay, this is the underflow condition. Now there are two possibilities, that at least a sibling has 2 keys, that means one extra, at least one sibling. If both of them are having more than one, then we can borrow from anyone, but at least one will work. Then this redistribution will be applied. And case number 2, that no sibling has 2 items, that means no siblings has more than 1 items, then we have to merge. Now this is the pictorial representation of redistribution and merge. Okay, so see the top left figure. Okay, see this right leaf has become empty. Since this is a 2 4 tree, there was minimum possible element 1 and we have deleted that, and this has become empty. Now I cannot keep it as it is. Now I find that the left sibling is having 2 elements. Okay, and this is parent. Okay, parent element. See, this is parent element, not the node. This node the parent node may contain more than 1 element, but this is the parent element which is actually taking care of these 2 leaf nodes. Okay. Now what I'll do, it's kind of rotation. This L element which has value greater than S, obviously, that's why it is appearing right of S. I will move this L up to the parent element, and this parent element P will move down to this empty leaf. And you can see the right side figure. Are you getting? It's kind of rotation. See, this L is pushing P. P is going down right side and L is moving up. Now see, this part of the tree where the B tree property was getting violated is now become okay.
Yes, sir. Yes, sir.
Okay. Now see the bottom figure, the left one. Suppose the leaf has become empty after deletion and it has only one sibling which is having only one element, that is minimum possible element. Now the redistribution is not possible. I cannot move L down and move S up, then this left leaf will become empty. Same underflow condition will come. So I cannot redistribute here. I cannot rotate. Then what I do? I will merge. And what is the technique of merge? I will pull down the parent element and I will merge it with the sibling which is having only minimum possible value, number of elements, like this. See the right side. Now you might find that after pulling the parent element down, it may so happen that the parent node may become underflown, because if parent node was having more than one element, then it is okay. But it may so happens in some cases the parent node was also holding only that value L, nothing else, because that was also possible. That was also satisfying B tree definition. In this case, what will happen? The parent node has become underflown. So in that case, we have to recursively apply the same technique, either redistribution or merging, as the case may be, and we may have to continue up to the root. Okay. Parent may become empty. The problem may recur all the way up to the root. And if it really recurs up to the root, then height of the tree will be diminished by 1. It is not always that will happen, but in some cases that may happen.
Yes, sir.
Okay,
Hmm.
okay, okay.
Hmm.
Now let us come to the real. I mean, this is the final one, that a root has become empty, so the height will become less than 1. One less by the earlier one. Fine. Let us see the real example. Okay. See, this is a 2 4 tree. You just check whether it satisfies all the properties of 2 4 tree. 2 4 means, as I have said, maximum number of children 4, maximum number of element will in a node will be 3, and minimum number of children will be 2. That means minimum number of elements per node will be 1. Okay. So this is the existing, the starting point. This is the B tree. Now I will illustrate the different cases of deletion by taking a deletion at different places. Okay. Let us delete item 21. This is the most trivial one. So 21, which appears at a leaf. Okay, see, in this figure, it may apparently it may look like that all leaves are not at same depth. Actually, they are. Okay, it is just the space constant. That's why I had to draw in such a way. You can easily check that all leaves are at the same depth. Okay, it's just the but looking at the first sight, it may appear that leaves are at different levels. You just check it. Okay. Now, as I've said, deleting an item uh, from any leaf will be trivial. The first part of the deletion process will be trivial. I'll simply delete it. I will remove it. Now, this is the second part is also trivial for this particular case, because the node was having extra element already. Extra, that means more than the minimum number of elements. So there is no underflow. Okay. So I don't need to do anything. Just simply delete 21. The updated tree will remain as a valid B tree or 2 4 tree. So no action is required further. Okay. This is the most easy kind of deletion we have seen. The second one, now let us delete the item or element 25. Where is 25? We can easily see, in order to search, I mean, obviously, I have not mentioned the actual first step of the deletion process is to locate the node. I have to employ MOS search to reach the particular node. I am just omitting that. Uh, you should not get confused that it is not needed. It is needed. I have to search 25 first. So I compare here, 25 is greater than 13. So I'll follow the right branch. Then I'll come here, right child of root. Here also the 25 is greater than the single key that is present 22. So I'll follow the right key, and then I'll search into this node, and I'll find that this node is the desired node. Okay. Now this 25 is not a leaf. I mean, the node containing 25 is not a leaf node. So what I have to do? I have to replace it with either in order predecessor or successor, and I have to delete the in order predecessor or successor, whichever I have considered, from its original place. Now let me replace it with the in order predecessor, which was 24. So actually this should not be written as 25. I don't need to swap. You can swap, but only replacement will also be 1. Now I have to delete that particular element from here. Okay. Now I will delete it simply. Now see, this is the physical node from where actual deletion will take place. Okay. And I have to start again afresh that whether this is leading to any underflow or not. And fortunately, there is no underflow after the actual deletion of this particular element from this node. And so we can stop here. No problem. So deletion of 25 is also over. Now next deletion of item 20 or element 20. So again we will locate, we will start from root, we will follow this, then we find that 20 is less than 22, so we will come here, then we find that 20 is greater than 18, so we will come here, and we find that 20 appears in this leaf node. Now there, after deleting 20, we see that there is an underflow in this leaf, because the leaf was containing only one element before the deletion. Now see which subtree we are interested now. This is the left sibling, the leaf containing 14 and 15. Then this is the parent element 18, and this is the actual node that was underflown. Okay, there is no right sibling here, so only one sibling, but fortunately that sibling is having more than one element, that means more than the minimum requirement, so we can borrow one from that node. That means we can redistribute it. So what will be the redistribution? 15 will go up in the parent, and the parent value will come here. See, in this way, what is happening? The MOA search property is preserved. That's why this distribution or kind of rotation we are performing. We cannot just move 15. Since we are borrowing from the left sibling, I cannot just take 15 from this left sibling to this node. I cannot do that, because that will violate the MOA search property, and that means that will violate the B tree property also. So that this kind of rotation is required. That is called the redistribution. 18 will come down and 15 will go up. Okay. So this will complete the deletion of element 20. Is it okay? Redistribution? Is it understood?
Yes, sir.
Everyone, please interrupt me if you are having any problem. Just check whether you have understood the redistribution. Okay. Shall I move ahead? Hello?
Yes, sir.
Yes, please interact. A little bit interaction is required. See, this is not the formal class. I am expecting that you are attending these classes based on your interest. Okay. So if you don't interact sometimes, it will be very difficult for me to continue. Okay. Please interact. Tell me that you are getting it or not, or suggest me something. Otherwise, it is very difficult. This is one-way traffic. Anyway, so next case can be observed by deleting 23. Now, where is 23? See, 23, we have to follow the right from the root, then right from the right child of the root, then left from the third, and here, this leaf. Third from the right. So if you delete 23, then see, this is another case where even if it has a sibling, the right sibling is not having any extra element. It is having just only one element, that means the minimum required element. So the redistribution cannot work here, because if we move down 24 here and move up 26 to its parent, then this right sibling will become underflow. Okay, so here what I have to do, we have to merge. Now what is the merging process? This the entire subtree will be merged to a single leaf, that the empty node, the parent, and the right sibling. So it will look like this. Okay, so this 24 will come here. Okay, just so the just take the steps. These two nodes will be merged together, and then actually these three nodes, not nodes, two nodes and one partial node, that means one element. That's why I have shown this in separate steps, because I am not merging these three nodes, because the other part of the node will remain there. Okay, I am not merging this node. This parent node is not getting merged with its uh, children. It is just these two children are getting merged, and this parent element is joining. Okay, so like this, and then the pointer manipulation will be like this. Okay, and fortunately the parent was also having, I mean, more than one element. That's why there is no underflow on top. So underflow doesn't recur. So we can stop here for this particular deletion. So this merging is clear.
Yes, sir.
Okay. So we are moving to different types of cases on this illustration. Now the last one, where we'll see that the extreme case will occur. That means there will be mm, redistribution and merging all the way up to root. Okay, so let's delete 18 now. Now where is 18? 18 will be greater than 13 and less than 22, greater than 15 here, this leap. Now as usual, since this particular leap node is containing only one element, obviously after deleting this 80, there will be an underflow. Okay, and unfortunately its sibling is also having only one element. So there is no scope of redistribution. We need to merge. So we'll merge these two nodes and we'll bring this parent here down. Now, as we can easily see, when we bring parent down, the parent node will become empty. So there will be underflow. Now, we'll see whether its sibling, who is the sibling of this parent node? This one, the right one, the shown in red rectangular, dotted rectangle. Now, here also we can see this is holding only one element, that means the minimum required element. So there is no question of redistribution here. We need to merge again. So we'll do that. We'll merge these two nodes into a single one, and we'll bring this parent element 22 down. And what happens? Since recursively it is going bad and bad, that means this particular node is also becoming underflown, and the left sibling, the one sibling it has, also having the minimum required element. So again redistribution is not possible, so we will merge, and in order to merge we will bring down this element 13, parent element 13 from the root, and in doing so what we will see, that parent node become empty. That is the extreme case which I was talking about when I was discussing the basic methodology for deletion. That means this will be, this particular node will be freed from the memory, and as a result the resulting tree will now have height 1 less than what was before deletion, this deletion of 18. Okay, so this was the extreme case, example of an extreme case where height of the tree gets reduced by 1. Understood? So hopefully I have been able to illustrate almost all possible cases uh, that may appear during deletion of elements. And remember, since I am illustrating on 2-4 tree only, because that is only possible in these slides. Okay, if we take a higher order tree, it will be very difficult to draw that tree on this PowerPoint slides. But don't fix your mind on this values 2 and 4, that means 1 and 3 number of elements. So you can easily check that the same thing will be true, same philosophy, same logic, same kind of redistribution and merging will be applied for any value of m. So B tree of higher order, just this underflow condition will be different. Here underflow means when the node becomes empty, but B tree of higher order, your node may become underflowed even if there are more than one element. It depends. The minimum number m by 2 uh, ceiling, less than m by 2 ceiling element means m by 2 ceiling minus 1 element means it is underflow, and you have to apply redistribution and merging accordingly. Okay. So that's all from my end today. Uh, and from next day, I would like to say that you give me at least one day before you want the class, because I need to prepare the slides. It takes time. This presentation was already prepared that day. That's why I can present it. I could present it within a very short notice. Sankita and Abhishek called me just 2.5 hours before.
Sir, actually, we were not aware that we wouldn't be having class today. Like, we knew that one class was not happening.
I understand. I have got that information, but what I am telling, since this material was already prepared, so it was possible for me today. But preparing these slides takes lots of time. Okay, so from next day
Okay, sir. Okay.
onwards, I will discuss and adjust your time and let me know at least one day prior to the actual class. Okay, so when can we have our next class? Can you tell me right now, or you will inform me later?
Sir, we could inform you after, like, at the beginning of the weekend or something like that. So then we will get an idea, actually.
Huh?
Sir, actually, we have, sir, is it possible if we could inform you by tomorrow or day after tomorrow?
Okay, that's no problem, because but it will only delayed. I want to conclude as early as possible, because you will be busy in your semester classes. As you move on to the new semester, your pressure will go up. Then you may not find enough time to attend the classes. So it is always good that you try to conclude as early as possible. Okay. So B tree discussion is over. I want to discuss little bit about graph. Okay, there are very interesting algorithms that you should at least have an idea. I would like to introduce basic terminology for graph. Then the BFS, DFS, those are very popular tool which can be used for solving many problems. Then I have a plan to discuss on topological sort and the MST algorithms, finding minimum spanning tree and shortest path problem. And those are very, very important thing. You will find application many where. So I would like to discuss all those stuffs on graph. And this is the most important part. And then a little bit on hashing I would also like to introduce, because hashing is also very important. And finally the counting sort, that integer sort algorithm, that will take one class, I think. So you try to provide the classes, arrange the classes as early as possible, because as I've said, I mean, when all the classes will start for your actual semester, this semester, you may not get enough time to concentrate on these topics. Okay. So I don't have any problem if you inform me tomorrow, day after tomorrow, no problem. But I would like to suggest that you make it as early as possible. Okay.
Okay, sir.
Okay. Then I'm stopping.
Our timetable, sir, for
Huh?
this.
Abhishek?
Sir, I have forwarded you the timetable, sir, for our this semester.
Yeah, see, timetable, it's the, see, it's not you plan based on your availability. What I'm saying that I am available uh, on this time, this 4 to 5:30. This is every day almost I am available right now. Okay.
Okay, sir.
And in the morning, uh, till now I have class from Monday and Tuesday and Wednesday. Monday. Apart from that, I am free. The 8th semester elective has not yet started. It will probably start from the next week. Okay. So if it gets started, then the first halves will be booked already. Then another slot is the evening slot. That means from 7:30 or 8 to 9, 7:30 to 8:30, like that. Okay. So I'll discuss. You just make a tentative plan. Then inform me. I'll choose the possible thing. Okay,
Sir,
Abhishek.
what about weekends, sir? Are you free on weekends?
We can see Sunday. I don't want to keep any class for you also. Saturday first half, because Saturday second half I usually have extra classes for first year students,
Okay, sir. So, sir,
the doubt clearing classes for second year student, first year student. Every Saturday I used to take, so that is blocked. Okay,
okay, sir.
Saturday first half from 10 to 11:30. That slot is possible, and even 4 to 5:30. Oh, 4 to 5:30 is not available. Okay. Okay, let me see the timetable, and Abhishek, you call me at night. We'll discuss and freeze the time. Okay.
Okay, sir. Okay. Thank you, sir.
Okay, then
Sir, about the
bye.
recording, sir, can we get the recording
Thank
for
you, sir.
the classes?
Recording. Uh, Let me see if I have. I forgot to record here. No. Uh,
No, sir, it's recording, sir. I think it will be in your Google Calendar. So if you have scheduled something, it will be in your Google
it is
Calendar.
already recorded. Oh,
Yes,
who
sir.
has clicked the recording? I have not clicked the recording. Anybody can click. Now,
Yes,
how
sir.
to share? It will. Huh?
Anybody
It will
can.
come. So it will come into your drive. If you organize the meeting, sir, it should come into your drive, sir.
Then how do I forward? I will just forward it to
Yes, sir. You could forward the drive link